You know, when we usually think about a nursery, whether it's like a room you carefully prep for a newborn baby or a really pristine greenhouse for delicate plants, there is this universal expectation of calm,
Oh, absolutely.
right? It's supposed to be warm, it's quiet, it is highly controlled. You plant a fragile seed in perfectly mixed soil, you water it gently, and you just wait for nature to take its peaceful course.
Right, because the environment is entirely engineered for stability. I mean, we've always operated on this assumption that creation, especially on a delicate scale, fundamentally requires a quiet, predictable space. You need that to allow things to grow layer by layer.
But what if you took that carefully curated greenhouse, picked it up, and dropped it right in the middle of a Category 5 hurricane?
Yeah, that's a wild image.
And what if, against all logical reasoning,
Hmm.
that violent storm didn't destroy the greenhouse, but actually caused it to spontaneously grow an entire massive forest overnight?
Which sounds impossible.
It does. But that is exactly what astronomers are seeing right now when they look up at binary star systems.
Yeah. It's just, it completely upends our fundamental understanding of how planetary creation works.
Yeah.
For centuries, we've looked at our own solar system, one calm, solitary sun, a nice, orderly disk of planets, and we just considered it the ultimate blueprint.
The gold standard.
Exactly. We assume that if you want to build a planet, you need a quiet neighborhood, but this new data is forcing us to ask if chaos itself might actually be the ultimate secret ingredient for mass production.
I am so excited to get into this today because we are looking at a fascinating deep dive into some new research that is actively rewriting the astrophysics textbook.
It really is.
So for you listening, here's our source material for today. We're looking at a great breakdown from technoscience.net that was published on May 18th, 2026. And that article unpacks a groundbreaking study published back on April 27 in the monthly notices of the Royal Astronomical Society. We've also got some really interesting visual data graphing stellar flux over time that we'll get into.
Yeah, that graph is crucial.
It is. So our mission today is to figure out how two star systems, which we previously just wrote off as way too violent to support planet formation, might actually be some of the universe's most efficient, hyperproductive planet factories.
We are literally talking about the mechanics of finding real-life Tatooines out there in the dark.
Yes, but to truly appreciate the magnitude of this paradigm shift, we have to look closely at the old dogma.
Right. For a very long time, the standard astronomical consensus was just that binary star systems were barren.
Totally empty.
Yeah. And the reasoning came down to the mechanics of how we thought all planets were made. It's a process known as core accretion.
Okay, let's unpack this. Or actually, let's break it down because I want to make sure the baseline physics are really clear for the listener. Core accretion is basically a bottom-up building process, right?
Exactly. So picture a newly formed star, and it's surrounded by a protoplanetary disk.
Just a big ring of debris.
Right. This disk is just a vast, swirling cloud of microscopic dust, gas, and little ice crystals. Now, in a single star system like ours, the gravity is centralized. It's relatively steady.
Okay.
So over millions of years, these tiny microscopic dust grains just gently bump into each other. And because the collisions are slow and gentle, static electricity and weak chemical bonds allow them to stick together.
So dust becomes pebbles.
Yes, dust becomes pebbles. Then pebbles slowly clump into boulders. Then those boulders smash together to form kilometer-sized planetesimals.
Wow.
And eventually, over immense stretches of time, you get a planet's rocky core.
It sounds incredibly fragile. I mean, it's like trying to delicately build a massive house of cards, you know?
That's the perfect way to look at it.
You need absolute focus and stillness in the room. If I'm trying to build a house of cards, having two fans blowing at me from different directions seems like a guaranteed way to fail.
Exactly. Core accretion requires a relative degree of gravitational calm. The particles have to collide at just the right slow speeds to actually stick.
Because if they hit too fast...
If they hit each other too fast, they don't stick. They shatter.
Oh, wow.
Yeah, obliterating millions of years of slow progress in an instant.
Which brings us to the big problem with binary stars. You don't have one central anchor holding everything steady. You have two massive gravity wells doing this constant high-speed waltz around a common center of mass.
Yes. And those two shifting gravity wells create immense, sweeping perturbations throughout the surrounding disk. You basically have constantly changing gravitational tides.
Like the two fans blowing at the House of Cards.
Exactly like the fans. The long-held belief was that this constant churning would whip the dust and rocks into a total frenzy, causing them to smash together at incredibly high velocities.
Right.
So instead of gently merging, the material would just shatter into dust over and over again, or just get flung entirely out of the system.
So if the established physics say the two stars create this gravitational blender that destroys any chance of slow, steady core accretion, why did astronomers suddenly decide this dual gravity wind wasn't a deal breaker?
Well, largely because our computational power finally caught up with our theoretical curiosity.
Ah, okay.
A team of researchers led by Matthew Teasdale at the University of Lancashire recently decided to push past the simple assumptions. They ran these highly detailed, high-resolution fluid dynamics simulations.
Specifically of protoplanetary disks in binary systems.
Yes, specifically in binary systems. They wanted to see the entire disk, not just the inner edge. And what they found was that the old assumption wasn't wrong exactly. It was just incredibly nearsighted.
Right, because they mapped out something they called a forbidden zone.
That's right. They confirmed that close to the two stars, the gravitational whipping is exactly as violent and destructive as we originally thought.
So no planets there.
None. In that inner region, the velocities of the dust and rock are just too high. The House of Cards gets blown away every single time. It is a strict, undeniable forbidden zone for planetary genesis. Nothing solid survives.
But protoplanetary disks are enormous.
Yeah.
I mean, they stretch out for billions of miles.
Massive, yeah.
So if the closed quarters are a forbidden zone, the logical next step is to look at what happens when you step just outside that area of total chaos.
And that is where the entire paradigm shifts. Beyond a certain distance, just outside that forbidden zone, the environment changes radically.
How so?
Well, you still have the vast disk of gas and dust, right?
Okay.
And it is still being actively perturbed by the shifting gravity of the two central stars.
Right.
But instead of destroying potential planets by smashing solid rocks together, this specific type of gravitational agitation triggers an entirely different mechanism. It's called gravitational instability.
Wait, I have to challenge the terminology here. Instability usually sounds like a bad thing when you're trying to build something.
Sure.
If I'm building a bridge, instability is a flaw.
Uh-huh.
How does an unstable, disrupted disk actually create a planet? Isn't that like trying to bake a cake during an earthquake?
I love that analogy, but we have to stop thinking about baking cakes or building a house of cards and start thinking about fluid dynamics. Have you ever made butter from heavy cream?
Yeah, sure. You put it in a jar and shake it violently.
Exactly. When the cream is just sitting still, it's a stable liquid. But when you vigorously agitate it, you force the fat molecules to slam together and compress.
Oh, I see where this is going.
Right. The violent mechanical agitation is the specific mechanism that forces the solid mass of butter to suddenly separate from the liquid. Gravitational instability in a gas disk works on a very similar principle.
Oh, wow, that makes so much sense.
Mm.
So the gravity from the two stars isn't a fan blowing away the cards. It's the arm shaking the jar of cream.
Precisely. The complex gravity of the binary stars creates these massive spiral density waves that ripple outward through the gas disk. The disk is literally buckling and compressing.
And gas is compressible.
Exactly. Because gas is highly compressible, the peaks of these waves become incredibly dense. The instability forces the gas to reach this critical threshold where the outward pressure of the gas is suddenly overpowered by its own internal gravity.
It just can't hold itself up anymore.
It can't. The smooth, continuous ring of gas violently fragments. It breaks apart into massive, distinct clumps of incredibly dense material.
Wow.
And because these clumps already contain so much mass, their own internal gravity just takes over in a runaway reaction. They rapidly collapse in on themselves.
So wait, they completely bypass the pebble and boulder phase?
Yeah.
They never build a rocky core first.
Never. This is a top-down process, not a bottom-up one. What's fascinating here is that they collapse directly from massive clouds of agitated gas into giant Jupiter-like planets.
That is wild.
And the most shocking part is the time frame.
Oh, right, because core accretion takes, what, millions of years?
Exactly. But gravitational instability can birth a giant planet in the cosmic equivalent of the blink of an eye. We're talking sometimes just a few thousand years.
So it's not a slow build at all. It's a sudden, violent, magnificent collapse into existence.
Exactly. And this brings us to an incredible quote from the study's co-author, Dimitris Stamatellos. When he was looking at the sheer volume of material collapsing in these simulations, he said, quote, "What we're discovering is that these systems can be extremely productive."
Productive. I mean, they aren't just forming one lucky planet out in the distance.
No, not at all. Because the entire outer disk is being agitated by those spiral waves, these systems are churning out giant planets in grand numbers. It is a mass production facility.
But I mean, if these systems are churning out giant planets at lightning speed in this gravitationally wavy environment, things are bound to get crowded, right?
No, incredibly crowded.
So what happens when all these newly minted massive giant planets start interacting with each other while the two suns are still pulling the strings from the center?
Well, this is where we see the darker, more chaotic side of this hyperproductive environment, because the brutal truth of the simulations is that not all of these newborn planets survive their infancy. Yeah, the extreme gravitational forces at play cause wild, chaotic orbital migrations. And very frequently, those complex interactions result in a planet being completely ejected from the star system.
Here's where it gets really interesting, because the physics of a planetary ejection are just mind-bending. It's like a cosmic game of musical chairs. But when the music stops, the loser doesn't just lose their seat, they get physically thrown out of the building entirely.
That is a brutally accurate way to put it.
But how does a massive planet just steal enough momentum to break the system's gravity and leave?
It all comes down to kinetic energy and orbital resonance. Think about how space agencies use gravity assists to send probes like, Voyager to the edge of our solar system.
Right, they fly it really close to Jupiter.
Exactly. The probe flies very close behind Jupiter, rides its gravitational wake, and essentially steals a tiny fraction of Jupiter's orbital momentum. The probe massively accelerates, and Jupiter slows down by an incredibly microscopic, unnoticeable amount.
But in these binary systems, we aren't talking about tiny probes. We're talking about multiple giant planets doing this to each other.
Exactly. You have 3, 4, or 5 giant planets all in crossing orbits, plus the 2 massive stars in the center. It is the ultimate three-body problem just scaled up.
A total mess.
Right. So when 2 giant planets pass too closely to each other, they exchange massive amounts of momentum. One planet gets decelerated and drops into a closer, tighter orbit around the stars.
Okay.
But the other planet absorbs all that stolen kinetic energy. It accelerates wildly. And if that acceleration pushes the planet past the star system's escape velocity, the star's gravity can no longer hold it. It is physically slingshotted out of the system forever.
Wow. The researchers in this study actually refer to these ejected planets as mons errants, or wandering worlds. We usually call them rogue worlds.
Yes. And the reality for a rogue world is absolute brutal isolation. Because of that violent gravitational kick, they are doomed to drift completely alone in the absolute freezing darkness of interstellar space.
Untethered to any star.
Completely untethered. They will never orbit a star again. They will never experience a sunrise or a change of seasons. They just float in the pitch-black void between star systems.
It is wild to think about a planetary factory that is so efficient, so wildly productive, that it just routinely shoots its own creations out into the dark as orphans.
It really is.
But let's pivot back to the survivors for a moment. If this chaotic churning process is as productive as the Lancashire team's models suggest, are we actually finding these surviving planets out there in the galaxy?
We absolutely are, and the observational data is beautifully validating the computer simulations. Astronomers have already confirmed the existence of over 50 circumbinary planets.
Circumbinary meaning a planet that has a wide enough orbit that it circles around both stars in the center rather than just orbiting one.
Correct. And what's vital is that several of these discoveries exist on very wide orbits, which aligns perfectly with where the models predicted the gravitational instability would force the gas to fragment.
So worlds with two suns, much like the famous planet Tatooine from Star Wars, might be far less rare than we ever imagined.
Oh, they might be incredibly common. The galaxy is likely teeming with them. But confirming their existence is an absolute triumph of modern observational astronomy because finding them requires us to measure incredibly minuscule changes in light.
Right, which brings up the visual source material we mentioned earlier. Let's explain how we actually detect these things. The study relies on this graph showing normalized stellar flux.
Yes.
Which sounds intimidating, but the underlying mechanism is fascinating.
It's based on the transit method.
Exactly. The transit method is the primary tool we use to hunt for exoplanets. Normalized stellar flux is simply a way to measure the brightness of a star over time.
So for you listening, let's visualize this. Imagine a graph where the vertical axis represents the total light we're receiving from a star system. We set the baseline, normal brightness of the stars, to the number 1.0.
Okay.
As time ticks by on the horizontal axis, the line remains a steady, flat blue line sitting right at 1.0. The starlight is constant. Exactly. But then, as you monitor this system, you suddenly see that flat blue line dip. It drops from 1.0 down to, say, 0.98 over a matter of seconds.
Right. And this is the critical distinction. It doesn't drop to zero. It doesn't cause a total eclipse. It's just a tiny, roughly 2% dip in the total light.
Which doesn't sound like much.
No. But to an astronomer, that microscopic drop is a massive, flashing neon sign. It means something massive has passed directly between our telescope and the star system, blocking a tiny fraction of the light.
That tiny dip is literally the shadow of a planet. But when you are looking at a binary star system, the math becomes astronomically more complex.
Because there are two stars.
Exactly. Because the two stars are also orbiting each other, they are constantly eclipsing one another from our perspective. So that baseline light curve is already fluctuating up and down as the stars cross paths.
So astronomers have to filter out the massive light dips caused by the stars eclipsing each other just to find that tiny, irregular 2% dip caused by a circumbinary planet crossing in front of them both.
It requires immense computational power and incredible precision. But when they find a transit signature that dips completely out of rhythm with the known orbital dance of the two stars, they know they've found a Tatooine.
That is staggering.
They've found a world orbiting the entire binary pair.
But this begs the question. So what does this all mean for you, the listener? Are we stuck just looking at lines dipping on a graph forever?
Well, if we connect this to the bigger picture, the answer is a definitive no. We are entering an entirely new era of observation. The brilliant thing about the Lancashire simulations is that they don't just tell us how these planets form, they give us a highly specific roadmap of where to point our instruments.
They know exactly where the fragmented disks should be hiding.
Yes, and astronomers are now preparing to aim incredibly powerful next-generation instruments right at these stellar nurseries. We are talking about using the James Webb Space Telescope and the Future Extremely Large Telescope, or ELT.
The ELT is going to be amazing.
It's going to revolutionize the field, because the ultimate goal isn't just to find more planets that finished forming billions of years ago. The goal is to point these immense telescopes at the disks surrounding young binary stars and actually observe the protoplanetary disks in the very process of fragmenting.
Wow. We want to catch the butter separating from the cream.
Exactly. We are moving beyond just running computer simulations in a lab. We are preparing to assist live with the chaotic birth of giant planets. We will be able to read the heat signatures of massive gas clumps undergoing gravitational collapse in real time.
That is just incredible. The idea that we can peer into these massive dust clouds and watch the mechanics of creation happening right in front of us.
It's a great time to be an astronomer.
Truly. So let's synthesize all of this, because the journey we've taken today requires a massive shift in how we fundamentally view the universe. We started out assuming that two-star systems were just barren, chaotic voids, a cosmic hurricane where the winds of competing gravity were just too violent to allow for the delicate, slow process of core accretion. But thanks to these advanced simulations and the incredibly precise observational data backing them up, we realized that the chaos is actually the engine of creation. The gravitational whipping doesn't prevent the planets, it compresses the gas.
It's the agitator.
Yes, it acts as the agitator that forces the disk to violently fragment and collapse directly into giant worlds. These binary systems are hyper-productive planetary factories, churning out Jupiter-sized planets so fast and so furiously that they occasionally slingshot their own creations completely out of the system, creating isolated rogue worlds that drift forever in the void.
It really proves that the universe rarely values our human sense of order. We assume peace is required for growth, but sometimes the most staggeringly productive environments in the cosmos are the ones that look like total destruction from the outside.
It makes you wonder what other assumptions we have completely wrong.
It really does. And I want to leave you with a final lingering thought to mull over. As we just discussed, we are on the verge of watching these planetary disks fragment live through our next-generation telescopes. Imagine walking outside tonight, looking up at the night sky, and knowing that a twinkling point of light isn't just a distant static star. It might be a live broadcast of a violent, swirling planetary genesis happening right at this exact moment.
That's a beautiful thought.
And furthermore, if we step back and look at the sheer numbers, binary star systems make up a massive portion of the stars in our galaxy. If these two star systems are this incredibly efficient at rapidly mass-producing worlds, Does that mean our calm, quiet, single-sun solar system isn't the standard blueprint for life, but actually the boring exception to the rule?
A quiet, slow anomaly in a universe defined by productive chaos. I love that. Well, thank you so much for joining us on this deep dive. Keep looking up, keep questioning what you think you know about how the universe works, and we'll catch you on the next one.